Good morning, students. Yesterday we have come across regarding qualitative analysis. Under qualitative analysis, different methods you have come across: volumetric analysis, gravimetric analysis. Under volumetric analysis, estimation of quantity of the substance present in the given solution. You come across in volumetric analysis different kind of titrations: acid base titrations, redox titrations, precipitation titrations, etc. And under volumetric analysis, acid base titrations. Today we are going to discuss about the acid base titrations and their graphical representation, change of endpoint at pH level, and significance of indicator. Estimation of acid versus base or base versus acid. As you know, if you take the acids and bases, they can they can be four types: strong acid versus strong base titration, strong acid versus weak base, weak acid versus strong base, weak acid versus weak base. Here, when strong acid versus strong base volumetric titration is done, so how the curve is appearing and end point. Example for strong acid versus strong base: sodium hydroxide versus HCl. 0.1 normal sodium hydroxide is treated with 25 ml of 0.1 normal hydrochloric acid. The pH value of the solution is measured at any intervals up to addition of 24.99 ml, 25 ml and 25.1 ml of sodium hydroxide. A graph is plotted of pH against volumes of sodium hydroxide added. It is seen that pH increases very slowly from 1 to 4 when such large amount of 24.99 ml of sodium hydroxide solution is added. However, the addition of small amount of sodium hydroxide solution, that is 0.01 ml, raises the pH value abruptly 7. This stage actually corresponds to the completion neutralization of the amount HCl taken initially, further addition of small amount, that is 0.01 ml of sodium hydroxide solution, further causes the pH to shoot up a value of about 10, because this addition of sodium hydroxide solution will convert the neutral solution pH 7 to alkaline pH value above 7. You can see the graph strong acid versus strong base. If you look at when you are going on adding the acid to the base, just now I told that up to 24.599 ml up to there is no change much. The pH value is varying between the 1 to 4 only. But when 24.5 after that 0.01 ml is added, there is a sudden change in pH value, that is 7. So the pH at which 7 the reaction is completed. Now solution is in neutral in state. After that, if you are adding 0.01 ml of solution, then pH changes about 10. So it will solution resultant solution is basic in nature. The indicator is suitable which undergoes change in this range of 4 to 10. Methyl orange, methyl red, bromo, thymol blue are used in such kind of titrations. Titration curve, a weak acid against strong base. Example, acetic acid versus sodium hydroxide. The titration curves shows that there is very little change in pH value, that is from 2 to 6. The volume added is just less than required for complete neutralization. The acid is taken. Just before the end point, addition of very small amount of 0.01 ml of sodium hydroxide suddenly alter the pH about, then this is the end point of the titration. The indicators usual should have pH range 7 to 10, pH range 7 to 10. Phenolphthalein pH range is 8.3 to 10 is best used for such titrations. You can see the curve acetic acid versus sodium hydroxide. The change in pH taking place above 7. The curve is not straight line, it is like S-type shape, and it beginning slowly the pH is going on increasing. Suddenly at the pH value 7, there is a sudden increase in the pH value. After that again pH value slowly increasing and remain constant. Titration curve, weak base versus strong acid. The titration curve of weak base, that is ammonium hydroxide with strong acid HCl, shows decrease in pH with addition of acid to base. The salt ammonium chloride formed during neutralization undergoes hydrolysis to give acidic medium. Therefore, the end point lies in the acidic range. The variation of pH takes place in the region from pH 3.5 to 7. Methyl orange, methyl red are the best indicators used in such titrations. You can look at the graph here, weak acid versus strong base, and here at beginning if you observe that the pH is more as the volume going on adding, what is happening, the pH value is more, goes on decreasing, and the pH value is decreasing means acidic strength is increasing, acidic strength increasing. Curve weak acid versus weak base. Since acid and base are both weak, the change pH along the whole length of the curve is gradual. There is no change observed, no sharp endpoint is detected. The titration curve shows change in pH 6 to 8. Phenol red ranging from 6.8 to 8.4 is used as an indicator for such titrations. You can see the graph. There is no clarity regarding curves, and the curves also not that much peak level where weak acid versus weak base. There is no significant pH change when titration is carried out weak acid versus weak base. Next, Radox titrations. A titration which deals about a reaction involving oxidation and reduction of certain chemical species. Redox titration curves. We need to know the shape of its titration curve to evaluate a redox titration. For Radox titration, it is convenient to monitor the titration reactions potentials instead of the concentration of one species. The Nernst equation relates a solution potential to the concentrations of reactants and products participating in the Radox reaction. Consider, for example, a titration in which a titrant in a reduced state A reacts with titrant in an oxidized state B. When A is titrant oxidation form, B is the titrant's reduced form. Reactions potentials, that is standard reduction potentials, is the difference between the reduction potentials for each of reaction. After each addition of titrant, the reaction between the titrant and the titrant reaches a state of equilibrium because the potential at the equilibrium is zero. The titrants and the titrants reduction potentials are identical. This is an important observation because we can use either off reaction to monitor the titration progress. Before the equivalence point, the titration mixture consists of oxidized and reduced forms, appreciable quantities of the titrants. The unreacted titrant concentration is very small. The potential is easier to calculate. If we use the Nernst equation for the titrants of reaction after the equivalence point, it is easier to calculate potential using Nernst equation for the titrants of reaction. Redox indicators. The vast majority of redox indicators are oxidizing or reducing agents themselves. Perhaps the principal exception is starch, which forms a blue complex with iodide ion and is frequently used as the indicator in iodometric methods. A useful visible redox indicators should possess the following properties. It should change color at the stoichiometric point of the titration. The color change should be sharp and involve intense contrasting colors. The indicator should be soluble, stable, undergo reversible changes. Indicators for Radox titrations. These are of three types. Self-indicators, external indicators, Radox indicators. Radox indicators are also known as internal indicators. Self-indicators. In some cases, one of the reactants in the titration act as an indicator. Such a reactant is called self-indicator. For example, during the titration, potassium permanganate taken in burette against sodium oxalate taken in conical flask. The solution of sodium oxalate remains colorless until the reaction is complete. You can see the reaction between the potassium permanganate and oxalic acid. First, off reaction of potassium permanganate. Two molecules of potassium permanganate in the acidic medium is combining with 3 moles of sulfuric acid and giving that potassium sulfate manganese sulfate plus 3 water molecules, 5 nascent oxygen atoms. So here manganese in potassium permanganate plus 7 state is there and change it to plus 2 state. Oxidation of reaction, 5 moles of oxalic acid is consuming 5 nascent oxygens which is produced by potassium permanganate and giving that 5 moles of water molecules, 10 moles of carbon dioxide. The overall reaction takes place 2 KMnO4 plus 3H2SO4 plus 5 COOH taken twice gives K2SO4 plus 2MnSO4 plus 8H2O plus 10CO2. So this is example for Radox indicator. However, as soon as the action becomes complete, that is when the whole of oxalate present in conical flask is completely oxidized, added permanganate solution. Further addition of a single drop of potassium permanganate solution from the burette imparts a pink color with the solution of conical flask. This indicates the end point there. Potassium permanganate itself is acting as an indicator. It is known as self-indicator. Now come to external indicators. Sometimes completion of the reaction is indicated by the use of a substance outside the reaction mixture. Such a substance is called external indicator. For example, potassium ferricyanide is used as an external indicator during the titration of ferrous salt solution with potassium dichromate solution in acidic medium. The use of potassium ferricyanide as an indicator is based upon the fact that the ferrous ions from ferrous salt reacts with ferric cyanide ions forming a deep blue color ferroferric cyanide complex. However, in the whole of the ferrous ions present in conical flask are oxidized by the progressive addition of dichromate solution from the burette to Fe plus 3 ions. The indicator will not give blue color with the solution. Next, Radox indicators. Radox indicator is a compound which can undergo oxidation and reduction reversibly, and the oxidized and reduced form have different colors in general. Oxidized form and reduced form, there is a equilibrium between them. For example, you can take diphenylamine is used as a redox indicator during the titration of ferrous ion with dichromate. The reagent has blue-violet color in the oxidized form and is colorless in the reduced form. Some important Radox indicators: ferrine, the complex iron 2 complex and related compounds can be used analytically in a variety of ways. One of its applications is as a redox indicator. The redox reaction shown, the red color is very intense. The color change is very sharp. The indicator action is reversible, although acidity does not enter into off cell. The acidity will affect the indicator. Next one, diphenylamine. The diphenyl 4-sulfonic acid function essentially the same as redox indicators. The main difference is that later compound is much more soluble in water. These indicators are particularly suited to the titration of ferrous ion with dichromate. The mechanism of indicator oxidation has been suggested. First, the diphenylamine is oxidized irreversibly to diphenylbenzidine. The later one compound would be used as an indicator further reversibly as a result of the added titrant and reaching the appropriate potential to the diphenylbenzidine violet species results in a color change of colorless to violet. The actual color shades will depend on the color of the other species in solution. The indicator can also be used for the titration of oxidizing agent such as cerium plus 4, permanganate ion MnO4 minus, chromate and vanadium oxide VO3 minus, ferrous ion. However, diphenylbenzidine is oxidized to other products and is not stable for long periods of time as an oxidizing solution.